Good morning, everyone. So today we are going to be spending a little bit more time with the fundamental theorem of similarity. And if you've been having trouble with this, don't worry. It's one of the harder concepts, and I promise we will get there. And once it clicks, it's pretty easy to use. So let's just try out a few things, and I'm going to review some of the concepts from yesterday. So if we're talking about the fundamental theorem of similarity in regards to K, which remember is our scale change, also is going to refer to our size change. So either one, our scale factor, scale change, our size change. Whoop, got to spell that right. Oh, hey, wouldn't be a surprise if I didn't from you guys, huh? Anyways, so if we're talking about this with K, here's how it's going to work. Now, we've been using fundamental theorem of similarity in regards to lengths this entire time. And what we've been saying is if you took any length in the first figure and multiplied it by K, it should give you a length in the second figure. So let's say that this is our example, and we know that the length of the side of one of the bases of our original is 3. And let's say that we know our K is equal to 4. I know it doesn't quite look like it is, but we're going to say that our K is equal to 4. Well, what happens then to that length? Well, you take the original 3, you'd multiply it by 4 to get your new 1. By the way, I know I am multiplying here because you can see it is an expansion. I'm getting larger. So 3 times 4 would be 12, which means that I could fill in this length as 12. And if I knew the units, which I do if I look down below, these are all in centimeters, I could add centimeters behind. So length in the first times whatever your K is will give you the length in the second. Now when it comes to area, like let's say the area of the top of the box, things are going to be slightly different because you're changing the length both this way and this way by a factor of K. That means rather than multiplying by K, we're going to multiply by K 2 times, which can be shorthand written as K squared. You can also remember that since you're in the second dimension, it's going to be squared like the units are squared. So what that means is if I have the area of the base that was originally 9, I will take my A times my K and fill it in accordingly. My original area, K squared here because I'm an area. I'll take my original area, which is 9, times my K value, which is 4, and square it because we're in the second dimension, and that gives me my area of my box, which is 16 times 9, and that gives us a final area of 144. And when we're looking at then volume, this is going to change one more time. So with volume, let's say my original box was actually a cube and its volume is 27 centimeters cubed. Well, in this case, since I'm changing length, width, and height, each of those is changing by a factor of K, that each one is getting multiplied by that K value of 4. So that means rather than multiplying by just K, I need to multiply every dimension by K. So I'm multiplying by K 3 times because I'm in 3 dimensions, and I can shorthand that as K to the third, right? Not 3K, but K to the third. K times K times K. So when I'm filling in my formula, I look for my volume formula. My volume formula tells me that I'm going to do A times whatever K is to the third. And since my A value here is the volume of my original box, 27, times my K value to the third, which K value is 4 to the third, I end up with an overall volume of 27 times 4 to the third, or, and this is going to be a big number here because things get large quick, 1,728. And of course, I should include units here since I'm talking about volume. I'm in the third dimension, so my centimeters would be cubed, and here my area, since I didn't have it there, would be centimeters squared because area is in the second dimension. So that's how these formulas work, and you should add this to your formula sheet so you can refer back to that. Now the next question is, how does the fundamental theorem of similarity work when we're talking about ratios? So let's look at a few ratios. So remember that when we're talking about these ratios, what we're usually talking about with ratio of similitude is something like this, like a 3:2, where the length in the first corresponds with the length in the second. Well, since this is length, what you're really doing is just showing a different version of k. Remember that k could have been written for this one as 3/2 or 2/3, depending on which is the pre-image. And as we move into our next ones with area, all that's going to happen is we are now changing not just one, but two of these. So I'd get a 3 squared to 2 squared. You can see how this is impacted in our k value. So if we're talking about k over in this column, what you're looking at here is a k value where 3/2 got squared, which, by the way, would be 3 squared over 2 squared, or 9/4. And you can still see the same numbers that would end up here. 3 squared would be 9, 2 squared would be 4, giving us a final ratio of 9:4. And if the k value, of course, was reversed, it would just be 2/3 or 2/3. This is the contraction version, and that would give us 4/9. So you can see how these kind of connect, where one gets squared, the k value is just going to show it as a single number, whereas the ratio is going to show it as the relationship between two numbers. So with volume, again, we have that same idea, where if you started with 3:2, in volume, since you're in the third dimension, what you're going to do is you're going to cube these, because you're looking at the change three-dimensionally. And that gives us a ratio of 27, or 3 cubed, to 2 to the third, which is 8. So 27 to 8 would be our end ratio there. So we end up with 3 different possible ratios that we might use, and 3 different possible k values, where here our 3/2 squared would be, well, or cubed would be 3 to the third, or 27, over 2 to the third, which is 8. Or, of course, if our k value was reversed and we were looking at a contraction, 8/27 would be that k value. So again, 3 options. You'll use this ratio when dealing with lengths, which is what we've been doing the whole time. But if you move into something that's talking about area, you'll square your ratio of similitude, or the relationship between lengths, to get a new one. Or if you're talking about volume, you'll cube that ratio of similitude to get a new one. So just make sure that you're changing both numbers and not just one. Let me give you a few examples of these two concepts. For the first one, let's talk about something where I know that k is equal to 28. That's a pretty big one. So I know that I'm doing a size change of 28. Now the question is, what will be the relationship between the areas? Well, don't forget that when we're talking about area, we know that area is going to be a times our k squared to get our b value. So that means I'm going to find my relationship in this part, where my 28 gets squared because it's an area, and I end up with a k value, or a relationship of area, of 28 squared. And that is the same as 784. How about this one? Let's say that our original k value is 9. I want to know the relationship between the volumes. What will that be? Well, in this case, I'm going to look at what my formula requires. I'm going to have a times k something is equal to b, and volume we know is k to the third. So looking at just the relationship here, remember I'm not actually trying to find links here, I just want to know what's the relationship between the volumes. I can fill in my 9 cubed, and that will give me my new relationship with volumes rather than just k, and 9 to the third is the same as 729. So these are just finding new, we can almost call them k values still, to work with. That being said, let's say that we do know some information about our ratios. So let's look at an example with ratios. If I have a ratio of similitude in which I know that 2 to 9 is our original relationship, it's our ratio of similitude, what will be the one for volume? Well, all you need to do in this case is, since volume is 3-dimensional, all you have to do is cube all the values in your ratio of similitude. So this would be 2 to the third to 9 to the third, and that gives us an answer of 8 to 729. So that would be the new ratio of the volumes. That should be how the volumes match up. Now, you could also have been told something about the volumes. So maybe I told you that in our volumes, they had a relationship where one was, let's go with 125 times as large as the other. Well, what this is saying is our k to the third was 125. So what would be just k? Well, take the cube root of both of these. And remember, you can find that in your calculator underneath the option of math by clicking math, go down to that 3, the square root, or actually, as it's properly said, the third root, and then typing in your 125 to get your answer. If you are unable to do that, by the way, you can always find the cubed root by raising the number to a fraction where you have 1 over the root that you want. So instead of the third root, you can do 1 over 3. And that will actually do the same thing. Just make sure you have this in parentheses if you're going to use this method, okay? And again, that gives you 5. So that means in this case, if the relationship between the volumes is 125 times as large, the relationship between the lengths, or just k, will be 5 times as large. Now, I've worked solely with expansion here, but you guys can use this with contraction, and I can even find, using only volume, what my relationship between areas would be with this last one, simply by squaring the 5, because the relationship between area is always k squared, and that would be 25 times as large. That's the review from yesterday, and what's going to come in the next video is a few more example problems in some harder concepts. So go ahead and check that out before you guys go through the practice problems for today, and don't be afraid to stop by for extra help if some of these things are still kind of difficult for you.